Okay, share my screen and make that go away. Here we go, chapter 7. Okay, so we didn't have lecture on Monday. Sorry, I can't remember what day of the week it is anymore. And in my announcement, I asked you guys to go ahead and work on these few problems here, writing reactions from a sentence. So hopefully you guys did that. Hopefully you've taken a look at these. You were given 3 of them. The first one says solid potassium chlorate decomposes to form solid potassium chloride and diatomic oxygen gas. The second reaction was solid aluminum metal reacts with solid diatomic iodine to form solid aluminum iodide. And then the third reaction that I wanted you guys to write from a sentence was when solid sodium chloride is added to aqueous sulfuric acid, hydrogen chloride gas and aqueous sodium sulfate are produced. So what I was hoping to have you guys do is to take these, you're given the information and turn this into a balanced chemical equation. So hopefully you were able to determine the formula for potassium chlorate, right? Using Nick the Baby Camel, you should have been able to get that chlorate is ClO3 with a -1 charge. Potassium is in group 1, so it has a +1 charge. So a +1 and a -1, right, means that when you pair these two together, you're going to get KClO3. Okay. Potassium chloride indicates that you have the chlorine ion, right? Chlorine is in group 17 or 7A. It has a -1. Potassium has a +1. Okay. And then diatomic indicates, the di indicates 2 atoms of oxygen in gas form. So that's your basic equation here. And then the next step is to balance it because we want a balanced chemical equation. We can see right away that this is not balanced. You have 3 oxygens here and 2 oxygens here. So we are not balanced, okay? And we also want to make sure we put the states of matter in. Now those you were actually given in the problem. You were told that it is solid potassium chlorate. You were told that it is solid potassium chloride and diatomic oxygen gas. So we want to put the states of matter in. And then finally, we want to balance it. And when we balance it, I started mine with putting a 2 here and a 3 here because I had 3 oxygens on one side, 2 oxygens on the other side. 3 and 2, okay, I know that my common factor, it's going to be 6. So I put a 2 here and a 3 here. Of course, by putting a 2 here, that does get me the 6 oxygens, but it also means I now have 2 potassiums and 2 chlorines. So my final step was to put a 2 here in front of the KCl. Okay, so there were 3 steps to this. The first was determining the formulas from the names and getting my base equation. Then I added in my states of matter, which were given to me in the problem. And then finally, I balanced the equation. Okay. My next example said solid aluminum metal reacts with solid diatomic iodine to form solid aluminum iodide. Remember that when you have a metal, right, by itself, that means it's not in a molecule, it's not bonded to anything. Diatomic iodine, right, diatomic, again, the di indicates that you have 2 atoms of iodine. And then solid aluminum iodide. Okay, again, that's an ionic compound. Aluminum is a metal with a charge of +3 based on its location on the periodic table. Again, it's in group 13 or 3A on your periodic table here. Iodine is in group 17 or 7A, so it has a -1. So we have a +3 and a -1, which means that the formula for aluminum iodide is going to be AlI3. Okay, AlI3. That's my basic equation. And then I'm going to put my states of matter in. I have solid metal, solid diatomic iodide, and solid aluminum iodide. So everybody's in the solid state. And then finally, my last step is going to be to balance this. I have 3 iodine on the right, 2 iodine on the left. Just like in the last one, that means I'm going to start by putting a 3 in front of the iodine and a 2 in front of the aluminum iodide. That will get me 6 iodines on both sides. But of course, putting a 2 in front of the aluminum iodide means that I now have 2 aluminums. And so I will need a 2 in front of the initial aluminum. Okay. Okay, so again, 3 steps: base equation, states of matter, balancing. Okay. And the last one that I asked you guys to work on when we for Monday was this one. Solid sodium chloride is added to aqueous sulfuric acid, hydrogen chloride gas, and aqueous sodium sulfate are produced. Okay. Solid sodium chloride. Sodium chloride is an ionic compound. Sodium is a +1, chlorine is a -1. So my formula will be NaCl. This is added to aqueous sulfuric acid. Remember that when you have an acid like this, if the ending is in IC, it came from the 8 ion. So the sulfuric acid came from the sulfate ion. Sulfate is SO4 with a -2. So sulfuric acid is H2SO4. Hydrogen chloride gas, chlorine is a -1, hydrogen is a +1, so HCl in the gas form. And aqueous sodium sulfate, remember that aqueous means dissolved in water. Sulfate, SO4 2-, either from memorizing or using Nick the Baby Camel. Sodium, Na+1. So Na+1 and SO4 -2 means that the formula for sodium sulfate is going to be Na2SO4. Okay, so there's my base equation with my states of matter as given to me: solid, aqueous, gas, aqueous. Okay, now we need to balance it. I could tell right away that this is not balanced. I have 1 sodium on the left, 2 sodiums on the right. So I'm not balanced. So the first thing I did when I was balancing this at home was I put a 2 here to balance my sodiums. Okay, but that also affected my chlorine. Now I have 2 chlorines. So then I put a 2 here, right, which fixed my chlorines, but that affected my H's. It turns out it affected it in a good way though, because by putting a 2 here, I now have 2 hydrogens and I had 2 hydrogens here. So that actually helped me to balance this. Okay. So again, this is a skill, this is not a new thing, right? This is actually review from the first half of the chapter, right? And a lot of this is review from previous chapters. Determining chemical formulas from names of compounds, that's from a previous chapter. From this chapter is this idea of balancing these equations and using the states of matter. Okay, so again, this is a little bit of review, a little bit of stuff that we've learned in the first half of the chapter. But now we're going to talk about what happens if I give you the reactants, but I don't tell you what the products are. So in the previous set of examples, you were told the whole reaction. If I have this plus this, I get this and this, right? And then you could write an equation. But what if I don't tell you what the products are? Well, the first thing is that understanding the type of reaction that you're dealing with is going to go a long way towards predicting the products. Think about things like a combustion analysis. Combustion reactions always have the same products. The products are always carbon dioxide and water. So if you recognize that you have a combustion type problem, right, then you'll know that your products should be carbon dioxide and water. In acid base, for example, if you're pairing an acid and a base together, remember that a neutralization reaction means that your products are always going to be salt and water. So again, that's going to help you figure out what the reactants are. Also, if you have 2 ionic compounds reacting together, this is often going to result in a double replacement reaction. So you know that 2 things are going to swap spots, and that's going to help you identify what the products are. So let's see, what does this look like, right? What if I give you the reactants? Can we figure out the products? So let's say you're given something like this. We have 2 ionic compounds, sodium chloride and silver 1 nitrate. okay, sodium chloride and silver 1 nitrate. And we want to know, right, what are my products? Okay. The fact that I have 2 ionic compounds is an excellent indication that I'm going to have a double replacement reaction. Okay, I know it's not a combustion reaction because combustion reactions are what happens when you have carbon and hydrogen in some ratio, and that is paired with oxygen gas. Well, we don't have any carbon-containing compounds here, nor do we have any oxygen gas. So this is clearly not a combustion problem. It's not an acid-base reaction, right? To have an acid-base reaction, we need an acid, and an acid is indicated by hydrogen. Well, we don't have any hydrogen. And remember that a base is indicated by the hydroxide ion. So this is not going to be an acid-base neutralization reaction. It can't be a single replacement reaction because remember, to have a single replacement reaction, you need something that's by itself. Well, both of these are molecules, right, with different elements. So it's not going to be a single replacement reaction. What else could it be? So that covers acid base, double, single. Oh, it's unlikely to be a combination reaction, right? Because this would be a rather large molecule, right? We have 2 metals here, 2 nonmetals here. So this is unlikely to be a combination. And it can't be a decomposition because in order to be a decomposition, you would need one thing breaking down into more than one thing. Well, we have 2 things. So this kind of leaves us as our only option is a double replacement reaction. Okay. So to understand what's going to happen in a double replacement reaction, we need to understand what happens when you put an ionic compound in water. Okay, and to understand that, I want to show you guys a short video very quickly here about what happens when you put an ionic compound in water. I've got it here. Can you guys still see my screen? Can you guys see the video I'm about to show?
Yes.
Yes, okay, awesome. All right. Okay, good. All right, so I'm going to play this.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Okay. So basically what happens when you put an ionic compound in water, okay, what happens is that the ions are basically ripped apart. So when you put sodium chloride in water, the sodium is positively charged, the chlorine is negatively charged. The water molecules come along and the oxygen ends of the water molecule, remember that water is polar. So the oxygen ends of the water surround the sodium side, and the hydrogen ends of water molecules turn around and surround the chlorine side, and they pull it apart. Okay, so when you put an ionic compound into water, what you're going to do is you're going to essentially undo the molecule. So remember in the previous chapter, we figured out how to put them together, right? We figured out, okay, sodium's a +1, chlorine's a -1. So I'm going to have 1 sodium for every 1 chlorine in this alternating shape. Okay, silver, this is silver 1 nitrate. So I have a +1. I have a silver who's willing to give up 1 electron, and I have a nitrate over here who's willing to take 1 electron. And so I end up with positive silver, negative nitrate, positive silver, negative nitrate. Okay, and that thing is also going to get ripped apart by the water molecules. So what we're going to end up with is back where we started, right? If I told you silver 1 nitrate, you would know, okay, I have a silver with a +1 charge and a nitrate with a -1 charge, and then you would figure out how to smack those two together. We're going to undo that, right? We're going to do the opposite. Now we're going to pull them apart. Okay. Once we have them pulled apart, then we can take a look at who's going to react with what. Now we want a new product, right? We want a new product. So I can't pair sodium and chlorine together because that's not a new product, right? We already had sodium and chlorine. So sodium and chlorine are not going to create a new product. That means that the sodium then has two choices. It can pair with the silver or it can pair with the nitrate. Anybody know, do you think that the sodium will pair with the silver?
No,
No, how come?
the two metals. I mean,
Yeah, they're two metals and they're both positively charged. So think about if you have two magnets and you try to bring them together. So if you have two north poles on a magnet and you try to bring them together, they're going to try to force each other apart, right? They're going to push away, repel. The same is true here. These are both positively charged. When you bring two things that have the same charge together, they repel. So the sodium and the silver would never get close enough to each other to form a compound. And also, they're both electron deficient, right? They've both given away an electron. So they're not going to want to pair up with each other. That means that my only choice is to pair the sodium and the nitrate. Okay, so one of my products is going to be sodium and nitrate paired together. That means that my only other possible compound is the silver and the chlorine, right? The silver is not, we already established, is not going to want to pair with the sodium. So we already said that that wasn't going to happen. And the silver isn't going to pair with the nitrate because that's what we already had. So my only option for a new compound is silver and chlorine. Okay, so now those two are going to pair together. And so that gives me this compound here, NaNO3 and AgCl. Okay, and again, NaNO3, I have a +1 and a -1. So this is a 1-to-1 relationship. And I have a +1 and a -1. So when these two pair together, I have a 1-to-1 relationship. Okay, so now the next thing we need to do is to determine what state is everything in. We were initially told that the sodium chloride is aqueous and the AgNO3 is aqueous. So we know these two, but now we need to know what state are these two in. Did they stay aqueous, right? Or have they turned into a solid? The way to predict that, the way to tell what state a compound is in, is to look at the solubility rules. Solubility rules tell you whether something dissolves in water or not. Okay, that's what solubility means. It tells you whether or not something dissolves in water. If something is soluble, so see here this first column, soluble ionic compounds. If something is soluble, that means it will dissolve in water. So its state will be aqueous. Okay. Again, if something is soluble, that means it will dissolve in water, and that means its state is going to be aqueous. If something is insoluble, right? This column here, insoluble ionic compounds. If something is insoluble, that means it will not dissolve in water and instead will become a solid. So remember, we talked about precipitation reactions, and precipitation reactions were a subcategory where you had two aqueous compounds and one or more of your products were in the solid state. So we had two aqueous compounds. If one of my two new products is insoluble, that means that I have a precipitation reaction. Okay. Now, I got this information and this from your textbook. So when you're doing the homework or the quizzes and you're trying to determine if something is soluble or not, that's where this came from. This particular table is directly from your textbook. Okay, so you'll want to bookmark that somewhere because you'll need it. Okay. All right, so let's look at our two products and see if we can determine if they're soluble or insoluble. So my first product is NaNO3. Okay, so I'm going to start with the soluble thing. Okay, according to my soluble, right, choices, I'm looking for ones that contain the following ions. Group 1 cations: lithium, sodium, potassium, rubidium, cesium. Okay, I have a group 1 cation, right? I have sodium here. Sodium is a +1, right? And it's paired with this nitrate. So that means I contain this ion and there are no exceptions. So that means that this is soluble. Okay? Anything that contains a group 1 cation will always be soluble because there are no exceptions to this rule. So it doesn't matter what you're paired with. If you're a lithium, sodium, potassium, rubidium, or cesium, you are soluble in water. So therefore your state will be aqueous. Okay, so the state of matter for my sodium nitrate is going to be aqueous. Now let's look at the silver chloride. Okay, silver is not a group 1 cation, so that doesn't help me. Okay, chlorine is a anion, right? We've got silver chloride, so we have a chlorine anion here. So anything with a chloride ion is soluble, except, now we're going to look in my exceptions column here, except if it's paired with a silver +1. So silver 1 chloride, silver 1 bromide, silver 1 iodide, right? Those are exceptions. Since it's an exception, that means it's not soluble. Okay, so anything else that's paired with chlorine, sodium chloride, calcium chloride, magnesium chloride, let's see here, aluminum chloride, copper chloride, nickel chloride, right? Anything else that's paired with chlorine is soluble, except silver, mercury, and lead. So since this is an exception, that means it's not soluble. So that means that the state of matter for this guy is going to be solid. Okay. So based on my rules, that means that this guy is aqueous and this guy is solid. So what does that mean? Well, that means that we have a precipitation reaction. We have a double replacement that is also a precipitation reaction because two things in the aqueous state forming one or more products that is a solid. Okay, so this is a double replacement reaction and a precipitation reaction. Okay, so this equation here that we have written is called a balanced molecular equation. We predicted the products, we determined the states, we made sure the equation is balanced: one sodium, one chlorine, one silver, one nitrate, one nitrate. So now we have created a balanced molecular equation knowing only the reactants. Okay, let's do another example. Aqueous potassium iodide reacts with aqueous lead-2 nitrate to produce what? So again, we have our reactants. We're told what our reactants are. We need to determine what the products are. So first we need to get potassium iodide. Potassium is a +1, iodine is a -1. So when we pair these together, potassium iodide pairs Ki 1:1. And it's aqueous because we were told that. Lead-2 nitrate, that means that lead has a +2 charge. Nitrate, using Nick the Baby Camel, is NO3 with a -1. So we have a -1 and a +2. Right? When you pair together a +2 and a -1, you get this formula, PbNO3, 2 of them, and it's aqueous. Right? So now we need to determine what they're going to produce. Hopefully right off the bat, you guys can rule out combustion. Right? Remember that combustion requires a carbon and hydrogen containing compound, as well as oxygen gas. We don't have either of those. It's not an acid base. Again, remember, to have an acid base reaction, you need an acid, which is going to have hydrogens, and you need a base, which is going to have your hydroxides. So it's not a combustion. It's not an acid base. It's not a synthesis or a combination. It's not a decomposition because we have two things here. So what do you guys think this is going to be? If it's not any of those, what kind of reaction is this?
A single replacement?
Oh, you're close. If it was a single, remember that one of these things would have to be by itself. It's not a single, it's a
Double.
Yep, it's a double, right? So remember, in order for it to be a single, that would be one thing swapping spots. So that would be if this was just K by itself, or if it was just I by itself, right? Then you would have a single replacement. But now we have two compounds, two molecules. So it's got to be a double replacement. Two things are going to swap spots. In order to determine who's going to swap spots, we need to break this thing down because these are ionic compounds and we need to see what kind of ions they come from. So again, we're just going to undo, right? Potassium is a +1, iodide is a -1, lead is a +2, nitrate is a -1. So those are the ions that we have present. We have potassium +1, iodine -1, lead +2, and nitrate -1. Anybody know why I have a 2 out here?
Because nitrate is being multiplied by 2 with the lead ion.
Yeah, exactly, because there's two of them, right? We have two nitrate ions. That's what that 2 tells me. It tells me that I have 2 of everything in the parentheses. So I have a 2 here just because it will make my life easier down the road, okay? Now, if you didn't write that here, it's not a big deal. It isn't going to affect anything you do here. I only wrote it here because it's going to make life easier down the road when we start balancing the equations, okay? But if you did not put the 2 there, it's okay. It's not wrong, okay? All right, so those are my ions present. Okay, again, we know that the potassium and the iodine are not going to pair up because that was a product. So it's not a new product, right? So that's not going to pair up, okay? The potassium and the lead, are those two going to pair up?
No.
No, because they're both positively charged. So they're going to repel, they're going to push away. So it's not going to pair up with the iodine. It's not going to pair up with the lead. That means the only thing left for this potassium to pair up with is the nitrate. Okay. Potassium is a +1, nitrate is a -1. So my new product will be KNO3. That leaves my only option now is for the iodine and the lead to pair up, okay? Because the potassium and the nitrate are going to pair up. Since it's a double replacement, that leaves my iodine and my lead to pair up. So my 2 new products are going to be KNO3 and PBI2. PBI2 because this is a +2 and this is a -1. Remember, when you're pairing ionic compounds, the charges have to balance. So you need 2 iodines for every 1 lead. Okay, so now we're going to determine our states and we're going to balance. Okay, so there's my unbalanced equation. Right? Oh, shoot. I just told you guys what the states were. We were supposed to look it up. Sorry, I didn't realize I had that in there. All right, determine states and balance. We know the states of the potassium iodide and the lead 2 nitrate because they were given. We need to know the states of the KNO3 and the PBI2. So let's go back and look at our solubility table. KNO3. KNO3. So starting at my soluble and working my way down, do I have anything here? Is this the group I'm going to look at? KNO3.
Yes.
Group 1
Yes.
cation.
Yep, I have a group 1 cation. I have a K, I have a potassium. There are no exceptions to that rule. So that means that that first compound is soluble. Okay, that first compound, KNO3, is soluble. My second compound was lead 2 iodide, PbI2. Okay, so that's down here, right? I have chlorine, bromine, and iodine. I have an iodine ion, iodide ion. Okay, but before I say, okay, yes, it's soluble because I have this iodine ion, I need to check my exceptions. Is my compound one of these exceptions?
Yes.
Yes, I have a lead +2. Since it's an exception, that means it's not soluble. So going back to my problem, okay, going back to my problem here, this is a solid. This is aqueous, this is a solid. So now I just need to make sure that my equation is balanced. Okay, we just need to make sure that the equation is balanced. Okay, I had 2 NO3s, so I put a 2 here to give me my 2 NO3s. This 2 here also affects the K, so I put a 2 here. So now I have 2K and 2K. But putting a 2 here also affects my iodine. Luckily, I had 2 iodines over here, so that actually helped. So now we're balanced. Okay, this is the balanced molecular equation. And again, we did it by knowing only the reactants. Okay, we did not know what the products were going to be. Okay, now a total ionic equation comes from a balanced molecular equation. So once you have your balanced molecular equation, once you've determined what your products are going to be, and you've balanced it, the total ionic equation comes from that. And what it is the total ionic equation show what's really happening in your reaction. Okay, to get a total ionic equation, we're going to break up all ionic compounds that are in the aqueous state. Because remember that when you have an ionic compound in the aqueous state, that means it's dissolved in water, which means that the water is going to pick apart all of the ions, okay? So to get a total ionic equation, we're going to break up all ionic compounds that are in the aqueous state. Because as long as they're dissolved in water, right, the water can pick apart and pull apart all those ions. Okay, we are going to leave alone, not touch, anything that's in the solid, liquid, gaseous state or covalent compounds in the aqueous state. Okay, so we're going to leave alone solids, liquids, gases, and covalent compounds that are in the aqueous state. Okay, so if anything has an S next to it, like this PbI2, anything with an L, anything with a G, or if it's covalent, right, and it's in the aqueous state, we're going to leave it alone. Okay. So we already did the first part, right? When we were determining our new products, we already tore apart the aqueous ionic compounds. So we're already halfway to a total ionic equation, okay? Remember this from the first part, right? We split the potassium and the iodine, and then we split the lead and the nitrate, and then we started looking at who's gonna pair. So if you go back to this slide here, right? We already did this part. We already split up the potassium and the iodine and the lead and the nitrate. So if you're organized, you'll see that when you're figuring out the new products, you're already halfway to an ionic equation. Okay. So that was that first part where we broke apart our ions. Now to get my total ionic equation, I just need to look at my products. Right? I'm going to look at my products. I'm going to break apart anything that's ionic and in the aqueous state. I'm going to leave alone anything that's solid, liquid, gas, right? Or covalent compounds. Okay, so I'm going to break apart, essentially the only things I'm going to touch are ionic and aqueous. Everything else I'm going to leave alone. Okay, so of my two products, I have this compound in the aqueous state. Am I going to break this up or leave it alone? What do you guys think? KNO3. Am I going to break it up or leave it alone?
Break it up.
I'm going to break it up because it's ionic and it's in the aqueous state. We know that it's ionic because this is a metal. Potassium is a metal. So remember I told you, you would need to be able to identify ionic versus covalent, right, fairly quickly. This is why. So this is ionic. Potassium is a metal. It's paired with a non-metal anion. So it's ionic and in the aqueous state. I'm going to break it up. What about this compound? Am I going to break this up or am I going to leave it alone?
Leave it alone.
Yeah, I'm going to leave it alone because although it's ionic, it's in the solid state. Remember that we are always going to leave alone solids, liquids, gases, right? If it's a solid, a liquid, or a gas, we're not going to touch it when we're doing our total ionic equation. Okay? So to get the other side, right, our new products were KNO3 and PBI2. Right, we break up the KNO3, leave alone the PBI2. Now, breaking up the KNO3 should be fairly easy because we already had it broke up on the left, right? So again, you're just going to rewrite it broken up. Leave alone the PBI2. Okay, so now we're almost there. Well, this is our ionic equation. We just want to make sure real quick that it's balanced, right? That's our last step. Just make sure that it's balanced. 2 potassium, 2 potassium, 2 iodine, 2 iodine, 1 lead, 1 lead. Okay, 2 nitrate, 2 nitrate. Okay, so you just want to make sure that it's balanced. Okay, this is what we call a total ionic equation. And that's literally all it is. You're just ripping apart all of the ionic aqueous compounds. Okay. All right, so we were working with an already balanced equation up here. So as long as you kept that, right, this balancing should be pretty easy. This is a total ionic equation. Oops. To get to a net ionic equation. Okay, so remember we said there were 3 types. There was the balanced molecular, the total ionic, and the net ionic. To get to the net ionic, you need the total ionic. Okay. The net ionic is the total ionic, but with something removed. And what we're going to remove is something called spectator ions. Anybody remember from your reading what a spectator ion is?
It's an ion on both sides of the equation.
Yeah, it's an ion on both sides of the equation that is not participating or changing. So think about like a sporting event. If you're a spectator at a sporting event, you're not playing the game. You're not really affecting the outcome. Okay. So spectator ions are ions that remain completely unchanged. And I do mean completely. So in order to be a spectator ion, you must have the same charge on both sides, right? So you must, if you're a +1 on the left, you have to still be a +1 on the right. You must remain in the same state. If you're aqueous on the left, you have to be aqueous on the right. Okay? If you're exactly identical, i.e. not changing at all, then you're a spectator. And to get the net ionic, we remove you. So looking at the potassium, I have 2 potassiums with a +1 charge in the aqueous state on the left. I have 2 potassiums with a +1 charge in the aqueous state on the right. That means that the potassium ions were completely unchanged in this equation. So those guys are spectators. Okay, let's look at my next ion. I have 2 iodide ions with a -1 charge in the aqueous state. I do not have 2 iodide ions with a -1 charge in the aqueous state on the right. So that is not a spectator. I have to keep it. Okay. I have 1 lead ion with a +2 charge in the aqueous state on the left-hand side. I do not have any lead ions in the aqueous state with a +2 charge on the right. So I have to keep it. Okay. On the left, I have 2 nitrate ions with a -1 charge in the aqueous state. On the right, I have 2 nitrate ions with a -1 charge in the aqueous state. So that is a spectator, right? That ion is unchanged. It is not participating in the equation. Whatever is left over is your net ionic equation. So this and this and this are what's left over. So my net ionic equation is 2 iodide ions with a -1 charge in the aqueous state plus 1 lead with a +2 charge in the aqueous state. And together that forms lead 2 iodide in the solid state. So that is my net ionic equation. Okay, so again, to get your total ionic equation, you're going to break up all of your ionic compounds in the aqueous state, okay, leaving alone everything else. Once you have that total ionic equation, to get the net ionic equation, we are going to cancel out anybody who is not participating in the equation. And by that, I mean an ion or molecule that is completely unchanged on both sides of the equation. That makes them spectators. Okay. All right, let's do another example because I know that there's a lot here, right? There's a lot to unpack here. So we want to give the balanced molecular, total ionic, and net ionic equation for the reaction of gaseous C2H4 and oxygen gas. So first, can anybody tell me what kind of a reaction this one's going to be? What category is this?
Single replacement.
Ooh, you're close. Look at my 2 products. My 2, or reactants, sorry, not my products, my 2 reactants. I have C2H4 and oxygen gas.
Is it combustion?
It's a combustion. Remember that combustions have carbon and hydrogen containing compounds and oxygen gas. So if we know it's a combustion, what are my products going to be?
Carbon dioxide and water.
Yes, exactly. Carbon dioxide and water. Anytime you have a combustion, you know, your products are going to be carbon dioxide and water. So since this is a combustion, we know the left-hand side, right? Now we can figure out the right-hand side. Okay. The next thing we need to do is balance the equation. So we have the base equation here, and we know that these guys are gaseous and this is gaseous. The products of this are always going to be gaseous as well. Okay, so we don't have solid carbon dioxide or solid water, right? Think combustion is an explosion, right? You're burning a carbon compound in oxygen gas. So in order to get solid water, well, that's ice, right? You're not going to get solid water out of an explosion. You're probably not even going to get liquid water out of an explosion, right? Think explosion, your gases, right? So this is my base equation. Now I just have to take a second and balance it. Okay, I have 2 carbons here. So the first thing I'm probably going to do is put a 2 here. Okay. And then I ended up putting a 2 here to get my 4 oxygens. But then I had to put a 3 here because I had 2 times 2 is 4 plus another 2 is 6. So I put a 3 here. Okay. So step 1, balanced molecular. I got that by understanding I had a carbon and hydrogen containing compound and oxygen gas. So my brain said right away, okay, combustion, right? It's not acid base. I don't have any acid or any base here. It's not combination, right? It's not decomposition because I have two things here. So it's not decomposition, right? Again, the big clue is this C2H4 and the oxygen gas. So once I know it's combustion, I know what my products are. It's not going to be double replacement because we don't have ionic compounds here, right? This is a covalent compound. Carbon and hydrogen is not an ionic compound. Oxygen gas is not an ionic compound, so it's not going to be a double replacement or even a single replacement. Okay. All right. So, before I go on, the question said give the total ionic and net ionic. So can anybody tell me what is the total ionic equation for this? Is there one?
No.
No.
No, right? Because in order for it to have a total ionic equation, you need ionic compounds. Are any of these compounds ionic?
Nope.
No, we have no metals here, right? No metals. So there just is no total ionic and net ionic equation. So if a question on the test asked you for the total ionic equation, the answer here would be none, right? There is no total ionic and no net ionic. Balanced molecular, yes. Ionic means that you have to have ionic compounds, which we don't have. Okay, let's do another example. Aqueous potassium hydroxide reacts with sulfuric acid. Write the balanced molecular, total ionic, and net ionic equations. Can anybody tell me from the clues in the problem, what type of reaction is this?
Acid base.
Yeah, exactly. Acid base. There's a key word here, right? Sulfuric acid. That tells me, oh yeah, I probably have an acid base, which is a subcategory of a double replacement. Okay, so we have potassium hydroxide and sulfuric acid. We know that the products of an acid base are always going to be salt and water. But even if you couldn't remember that, this is a double replacement, right? Remember that acid base is a subcategory of double replacement. So hopefully we could figure out kind of what's going on here. Okay, so the potassium, right, is going to swap spots with this hydrogen here because this hydrogen and this hydroxide are going to get together to form water. That leaves the potassium to pair with the sulfate. Okay, so the products are salt and water. Okay, and we know that the hydroxide and the hydrogens are going to pair together. That leaves the potassium to pair with the sulfate. Okay, so we're going to pull hydrogen ions and hydroxide ions, and we're going to pair those together to make water. That leaves potassium and sulfate. Potassium is a +1, sulfate is a -2. So we're going to get K2SO4, right? 2 potassiums for every 1 sulfate. And then water, right? We know the formula for water is H2O. Okay, so you could figure it out because hydroxide's a -1 and a hydrogen ion is a +1, but hopefully we know that water is H2O. Okay, water is a liquid, right? Water is not an ionic compound, so you don't need your solubility table for that, right? You don't need your solubility. Anybody know why isn't the water a solid or a gas? How do I know it's liquid and not a solid or a gas? How do I know it's not a solid? What would have to happen for my water to be a solid? Anybody? How do you guys get solid water in the summer when you need your lemonade to be cold? How do you get solid water?
Because we're not changing the temperature at all.
Yeah, in order to get solid water, we have to freeze it, right? Another name for solid water is ice, right? In order to get ice, you'd have to freeze it, right? These solutions are both dissolved in water, right? In order for that to happen, the water has to be liquid. If the water was solid, that would be ice, right? There wouldn't be any reaction going on. Okay, same thing with the gas, right? It's not going to be a gas because the water, right? These are in aqueous states. These are dissolved in liquid water, right? That's what's going on with my solution here. I have 2 ionic compounds dissolved in liquid water. So the water is not going to suddenly turn into a gas, right? Unless we do like a combustion and heat it up, right? Explode it. It's not going to turn into a solid because we'd have to freeze it. So I know that my water is a liquid without even looking at my solubility table. Now this guy, right, I'd have to look at my solubility table. Now I didn't pull the solubility table because, right, look at that initial ion, right? Where is this ion found on the periodic table?
Group 1.
Group 1, right? Are there any exceptions to the group 1 solubility rule?
No.
No. So if we go back and just do a quick look here, anything with the group 1 cation is automatically soluble, right? So anything with a lithium, sodium, potassium, rubidium, or cesium is automatically soluble. That's one of those rules that you guys should just get comfortable knowing. It'll make your life a lot easier if you don't have to constantly keep looking it up, right? Anything in group 1 is automatically soluble. Okay, so I didn't even have to look that up. I knew that this was going to be aqueous because of that group 1 ion. So putting this together in my balanced molecular equation, I have 2 KOH aqueous, H2SO4 aqueous, 2 liquid water, and K2SO4 aqueous. Now, to get my total ionic, I'm going to start looking at what should I break up. Okay. So what am I breaking up here? Am I going to break this guy up, the KOH?
Yes.
Yes, that's an ionic compound in the aqueous state. What about this guy? Am I going to break this guy up?
No.
Ah, so you are correct that the answer should be no, right? Because what kind of a compound is that besides an acid?
Covalent.
It's covalent, right? Technically, that is covalent because hydrogen is not a metal, right? So you, by the rules I have given you, you are correct that you would not break that up because it's covalent. However, we're about to find out that acids are the one exception to that rule. Anybody know what the definition of an acid is? Anybody remember that from the reading? Anybody remember that? Okay, so that's something you guys definitely want to go back and look up. The definition of an acid is called a hydrogen donor, meaning it donates hydrogen ions. So acids are the one exception to that rule about covalent compounds, okay? Acids, when they go in water, they like to shed their hydrogen ions, okay? When you get into Chem 2, you're going to learn an awful lot about acids and why some of them donate more of their hydrogen ions than others. But for now, suffice to say, if you see an acid in water, it's the one exception to that rule about those covalent compounds. Okay, so acids in water, we do break up. Any other covalent compounds we leave alone, okay? But if it's an acid, we are going to break it up. What about this guy? Are we going to break this guy up?
No.
No, because it's a liquid, right? Remember, we leave anything in the liquid state alone. If it's in the solid, liquid, or gaseous state, we leave it alone. Okay. What about this guy?
Yes.
Yes. Okay. So we're going to break this guy up. We're going to break this guy up, and we're going to break this guy up, and we're going to leave this guy alone. Now, again, when you were figuring out the products, right, when you were figuring out the water, which is this H2 and this OH, you already kind of broke this up. So half of the work is already done, right? You already broke up the potassium and the hydroxide because you knew that the hydrogen and the hydroxide were going to pair together. So these two things. And then we knew that because it's a double replacement, that the potassium and the sulfate were going to end up together. So this part you already did, right? You already broke that down when you were figuring out what our new products were going to be. Now we need to move over to the right-hand side. Again, remember, we're going to leave this alone. The only thing we have to break up is the K2SO4. Again, you already had this thing broken up when you were on the left-hand side. So breaking it up on the right-hand side shouldn't be too tough, right? So we're going to leave the water alone, and then we're going to take this and put it back into its ions. So back into positive potassium ions and negative sulfate ions. And somehow my little AQ moved over here. It should be here. Okay, so this is my total ionic equation. Again, I got that the first half of this from what I did in the previous step. The second half, I'm leaving alone the water, and then I'm just breaking this guy back up. And we already did that in the beginning when we were figuring out how to swap things. Okay, so this is my total ionic. Now, to get my net ionic, I'm going to start canceling things. Let's take a look at the potassium ion first. Can I cancel that or should I keep it?
Cancel it.
Cancel, right? I have 2 potassium ions with a +1 in the aqueous state on the left, and I have 2 potassium ions with a +1 in the aqueous state on the right. So I can cancel that. Okay. What about the hydroxide? Can I cancel those?
No.
No, I don't have any hydroxide ions on the right. What about my hydrogen ions that came off of my acid? Can I cancel those?
No.
No. How about my sulfate ions, my SO4 minus 2s? Can I cancel those?
Yes.
Yes, I can. Okay. So what am I left with? Well, I'm left with 2 hydroxides in the aqueous state, plus 2 hydrogen ions in the aqueous state, and that's giving me 2 water molecules. So the majority of your acid-base reactions, the net ionic is going to be this, right? The only time that you would not get this is your net ionic, hydroxide plus hydrogen giving water. The only time that that would not be your net ionic is if you had a compound over here that formed a solid, right? So if you had something like silver, right? Silver chloride, something like that, then this would become a solid. Then you would have basically nothing would cancel out and your net ionic and total ionic would be exactly the same because nothing would cancel. Okay. If you do not have a soluble salt, right? If you do not have a soluble salt, right, then nothing cancels and they're the same. If you have a soluble salt, right, anything with the potassium, anything with a lithium, anything with the sodium, right, then your net ionic is always going to be hydroxide plus hydrogen gives water. Okay, so a little trick to make your life a little bit easier, right? Make this a little faster. If you have a soluble salt, right, you're always going to have hydroxide plus hydrogen ions giving water as your net ionic, and then you just have to balance it. If you have an insoluble salt, right, something with a silver, a lead, right, then your net ionic and total ionic are going to be exactly the same because nothing will cancel. Okay, so just a little trick to make your life a little bit faster. Right? Acid-base reactions are nice because the net ionic is always hydroxide plus hydrogen gives water for a soluble salt. For an insoluble salt, nothing cancels. So far, so good, right? This is, I think this is a fairly straightforward topic if you're comfortable with formulas and ionic compounds. Anybody stuck or lost or like, what the heck is she talking about? No? I'm going to take it that everybody's good. Keep in mind, if you don't want to speak up now, and I understand, the desire not to speak up in front of the whole class, please feel free to reach out to me via STEM 411. I'd be happy to do a tutoring session with you if you're stuck on this topic. It's a pretty big topic. You will see this on the exam. Okay, there will be something like this on your test. All right. So the next thing we want to talk about is something that's very similar to what we just talked about. Okay. These are redox reactions, which remember is another subcategory, right? Single replacement reactions are always redox reactions. Other types of reactions can be redox reactions, but you can't tell just by looking at them. Okay? But a single replacement reaction, you can always tell that that's a redox. Okay? Redox reactions involve the transfer of electrons. So electrons are being transferred from one thing to another thing. Oxidation refers to the loss of electrons, and reduction refers to the gain. So because we have a transfer of electrons, somebody is losing those electrons and somebody is gaining, right? Think your ionic compounds. Metal cations lose electrons, non-metal anions gain electrons. So we've already been talking about redox, right? But now we're going to explore, we're going to dive down a little deeper into what that looks like. We're going to look at the actual transferring of electrons from one thing to another. Okay, so again, keep in mind that oxidation refers to the loss of electrons. Reduction refers to the gain of electrons. There's a couple of little phrases you can use to help that stick in your head. Oil rig is what I've heard some students say, and that stands for oxidation is loss, reduction is gain. Okay, so you can use that to remember. The one I learned in high school was Leo the lion goes grr. Leo for loses electrons oxidized, gains electrons reduced. I don't care how you remember it, but you'll need to remember that something is oxidized if it's lost electrons, and something is reduced if it's gained electrons. Okay, so oxidized, loss, reduced, gain. Again, single replacement reactions are always redox reactions, but not all redox reactions are single replacement. So we're going to see that sometimes other types of reactions out there are also redox. Okay. So when you're looking at a reaction, if it's a single replacement, you know immediately it's also redox. All other reactions, we're going to have to figure it out. Okay. So how do we figure it out? How do we know if it's not a single replacement? How do we know if it's a redox? Well, in order to determine if any electrons have been transferred, we have to know the oxidation state. Oxidation state is fancy speak for what would the charge be on an atom if it had a charge. So what you want to think about is a couple of things, because we've been talking about oxidation states and you just didn't know it, right? We've been talking about this for a while now. We just didn't call it that. For ionic compounds, right? Metals, right, in group 1 +1, metals in group 2 +2, right? Fluorine, chlorine, bromine, usually a -1. Oxygen, sulfur, usually a -2. Nitrogen, phosphorus, -3, right? So these guys, right? Another way to think about it is think about when we did Lewis structures, we did formal charges. I don't know if you guys remember that, but we calculated the formal charges. Okay, that also makes it easy to predict the oxidation state because the oxidation state and formal charge are usually the same thing. Okay, so let's take a look at the rules for determining oxidation state. Okay, so first, rule number 1, and this is really important. An atom in an elemental substance always has an oxidation state of 0. So now what do I mean by that? What is an atom in an elemental substance? So I'm going to end this here and I'm going to pull up my whiteboard real quick on Zoom. Oh, here it is. Okay. Whiteboard, here we go. All right. So an atom in an elemental substance refers to a substance where the atom is by itself, meaning it's not bonded to anything else. Okay, so by that, I am referring to things like metals, right? Sodium, lithium, copper, right? Iron. Anytime you see, like when we were doing the word problems before where we were writing them and you saw like zinc metal or aluminum metal, right? These guys are all in their elemental states, okay? The reason that we know that, come on, it won't let me move it. Oh, sometimes I hate the whiteboard here, okay? The reason that we know that is that there is no charge to indicate that this is in the ionic state. Also, other thing you want to look for is the little S, right? So if we go back to our slides here for a second. Okay. If we go back to our previous examples, Okay, here, solid aluminum metal, right? This is not an aluminum ion in the aqueous state. This is aluminum solid, okay? Solid diatomic iodine, okay? This is in the elemental state. It's iodine by itself. It's not bonded to anything else. It's aluminum by itself. It's not bonded to anything else. Let's look at this reaction. This oxygen, diatomic oxygen, it's oxygen bonded to itself, okay? Anytime you have, let me see if I can find any more. Anytime you have an element by itself, I'm not seeing any others. Anytime you have an element by itself, it is considered elemental. So for example here, H2 gas, right? That's hydrogen bonded to other hydrogens. Therefore, it's elemental. The zinc in solid form, that is elemental, okay? None of these examples here are elemental, right? This is carbon bonded to oxygen, carbon bonded to hydrogen, aluminum bonded to oxygen and hydrogen, chromium bonded to carbons and oxygens, not elemental, okay? So anything that is by itself, okay, and not bonded to anything else is considered elemental. This includes things like diatomic oxygen, right? Like O2, diatomic chlorine, Cl2, right? Even things like sulfur likes to form a molecule where 8 sulfurs bond together. This is considered elemental, okay? The reason why it can't possibly have a charge is, remember that the charges need to neutralize each other. So if we have 2 oxygens bonded to each other, and we have this molecule here, we have 2 oxygens bonded to each other. Normally, an oxygen in an ionic compound forms a -2, right? So let's just say that this oxygen formed a -2. This oxygen cannot also be a -2. Why not? Why can't I do that?
Because then they would repel each other.
Yeah, they would repel each other, and we wouldn't have the octet rule, right? Remember, we had to have the octet rule where everybody had 8 valence electrons. There is no way to do this molecule where they both end up with a -2 formal charge and we satisfy the octet rule. So it's just not possible. This guy would have to be a +2, right, in order for these two things to balance out, and that doesn't happen. I remember when we drew Lewis structures, right? We didn't want formal charges if we could avoid it. So the only way for this to work is for the formal charges to be zeros. Okay, so this does not have an oxidation state of -2 and this of +2. The oxidation state is 0. Same thing with the 2 chlorines. Right? When you get 2 chlorines, they bond together with a single bond, right? And then each one has its valence electrons here. Okay. If we were to put a -1 charge on both of these, right, that would not work for a variety of reasons. Number one, because they would repel each other, right? Remember that 2 atoms of similar charges would repel each other, so they wouldn't bond, right, if they were pushing each other away. Overall, this molecule would have a -2 charge, so this would have to be an ion with a -2 charge, and we'd have to have a formal charge on both of these. Our other option would be, well, what if we made this a +1? Well, again, that's not possible. So what we have here is 2 chlorines, each with a charge of 0, right? It's the only way to make this work. So anytime you have something bonded to itself, right? Anytime you have something bonded to itself or a metal that's just alone like this, that is what we call the elemental state. If something is in the elemental state, its oxidation state is 0. Okay, so going back here to our slides, anytime you have something by itself in the elemental state, its oxidation state is going to be 0. Okay, so rule number 1 for oxidation states are that anything that's by itself or bonded to itself is considered in the elemental state, and the oxidation number is 0. Okay, that's really important. This is probably one of the most important of the rules. Okay, anything that's by itself, right, is 0. Okay. Rule number 2 says that the oxidation number of a monatomic ion is equal to the ion's charge. So if you see, instead of these guys in the solid form, so instead of seeing sodium solid, right? Oops, sorry, in an equation, right? If instead of seeing this, you see this. Sorry, it's hard to draw on this little thingy here. If you see this, right? Sodium with a positive charge in the aqueous state. Well, now the oxidation state is given to you. They're telling you that the oxidation state on this sodium is a +1. Okay, if you were to see lithium, right, instead of this, okay, if instead of that you saw lithium with a +1 in the aqueous state, if instead you saw this, now they're telling you that the oxidation state on the lithium is a +1. So examples of this. So let's go back here. Oops. Okay, so let's go back here to some of these examples that we've done in the past. Here we go. So looking at some of these, for example, okay, now when you see this potassium +1 aqueous, that guy has an oxidation state and it's not 0. The oxidation state of that potassium ion is +1. The oxidation state of this iodine is -1. The oxidation state of this lead is +2. The oxidation state of this whole ion is -1. Now we're going to talk about in a minute how to figure out what it is specifically on the nitrogen and the oxidants, but the whole thing is a -1. Okay, so whenever you see an ion like that has the charge written up here next to it, that is telling you what the oxidation state is. So the oxidation number of a monatomic ion, a single ion made up of a single atom, is equal to whatever the charge is. No thinking necessary. Okay, so again, the first 2 rules. Oxidation number of an atom that is by itself or bonded only to itself is always 0. Oxidation number of a monatomic ion is equal to the charge you're given. Okay, and it is now, I just realized it's now 10:46. So I'm going to go ahead and stop here. This is where we're going to pick up on Monday. We're going to continue talking about oxidation numbers and how to determine them. Okay. Again, before I forget, just a quick reminder, guys, I'm going to push the homeworks back. So you will not have an assignment due this Sunday. I'm going to push it back to next Sunday. We have plenty of time. We're moving along at a really good pace. We're not going to be finished with chapter 4. And so I don't want to try to force you guys to do those later homework problems because some of them get very complex. So I'm going to push the due date back on those. Everything else, you will have a course ticket due on Monday. Whatever reading assignments are out there, those due dates are not going to change. Okay. I am, however, going to push back the Cengage homework. Okay, I'm going to push that back by a week. Please be working on your quizzes, right? Please be keeping up with the material. We're almost done with the class. We just have to survive this chapter we're on now. And then chapter 8 is really short. Okay, it's much shorter than chapter 7. And once we get through that, we'll be through the class. For those of you who are doing really well, congratulations. If you can keep your A, right? If you can keep your A, you are exempt from the final exam. So this is now your kind of opportunity to make that one last push and, you know, see if you have a B right now, maybe you can pull it up to an A so you don't have to take the final. Any questions for me before I let you guys go? No, if not, have a wonderful weekend, guys, and I will see you on Monday. And don't forget your course ticket. I'll post it up here in a minute. Bye, Mary.